Welcome to Study Loop.
So now we'll work on problem 108 from chapter 17 relating to complex ion equilibrium. So here we're told that different solutions of silver nitrate and sodium cyanide are mixed together. And after the solution reaches equilibrium, what concentration of silver plus remains? So what we need to do first is write down our equation of what the precipitation will happen, or which reaction will happen. And so we have silver plus aqueous from the solution, and then also 2 cyanide will react to form silver cyanide. Now we know this question is a complex ion problem because it's listed so in our book. So we can find data for this from the table in the book. So first we need to calculate the initial concentration of silver and cyanide. And so this is equal to the concentration times the volume, so 0.120 liters times 2.8 times 10 to the minus 3 molar divided by the total volume, which is 0.120 plus 0.225. This is the volume of both solutions. When we do this calculation, we get 9.74 times 10 to the minus 4. And for cyanide, the initial concentration will be calculated the same way. The volume of solution times concentration times total volume, divided by total volume. And this gives us 7.39 times 10 to the minus 2 molar in both cases. So now we'll open up a new pages, keeping these concentrations in mind, and draw an ice table. So the relevant species are silver plus, CN minus, and the complex ion. And so we'll have initial change in equilibrium. Initial is equal to 9.74 times 10 to the minus 4 for silver, and 7.39 times 10 to the minus 2 for cyanide, and then none of this. So since a parameter which I failed to mention on this page is Kf, which is the rate of formation of this. And this is equal to 1 times 10 to the 21. So this is a very large value, which means that this formation here is very favorable. So since this is very favorable, and this is present in much smaller values than the cyanide ion, we're going to approximate that almost all of this is leaving, is going to react to form the ion. We do the same thing here, minus 9.74. Times 10 to the minus 4 times 2, since we need 2 cyanide ions. And then over here, we're going to say that we're achieving almost all of this concentration. So now we're going to, we can just do the calculation, subtract from the top and bottom, 10 to the minus 2. Here the concentration will be about 9.74 times 10 to the minus 4. Here we're going to let X equal the equilibrium concentration of silver. So we should be close to 0, since we're saying that almost all of it is being used. So I'll open a third page so we don't get too crowded, and we'll write our term for Kf. Now, like any equilibrium constant, this is going to be equal times to product divided by reactants. So in this case, this is our product, and our reactants are silver plus and cyanide minus squared. And this is equal to 1 times 10 to the 21st power. So what we're going to do is we're going to put X in for the silver plus concentration, and then we can plug in all the rest of our values. So we plug in our value of concentration here and here, and then we solve for X. And X will be equal to 9.74 times 10 to the minus 4, which is our concentration for silver cyanide anion. And then our Kf has moved to the bottom, 1 times 10 to the 21st. And our concentration of cyanide is 7.20 times 10 to the minus 2 squared. So when we perform these calculations, we get X is equal to 1.88 times 10 to the minus 22 molar as being our concentration of silver at equilibrium. This is our answer. Now, just to double check what we did previously, this value that we obtained, 1.88 times 10 to the minus 22, is much, much smaller than 9.74 times 10 to the minus 4, which was our initial concentration. So we can say, because this is so much smaller, we're saying that the approximation that we used all of our silver is valid. Since we had such a large Ks value, we could assume this at the beginning, but now we can double check and make sure that it's